In this lesson, you will learn how to factor the greatest common factor from a polynomial. A GCF is the largest factor that two or more terms have in common. To be a greatest common factor, it has to be the largest factor. So sometimes you can have a common factor of a 2, but you need to look again and see maybe if the greatest common factor, the largest factor, is really a 4 or maybe an 8. And they all have to have it in common. If two of the terms have that 4 in common, but that last term does not, then it's not a common factor. It has to be the greatest thing that all terms have in common. So let's look at our first example, number 1. We have 12x squared plus 9x plus 3. So we will start this by doing prime factorization on all three terms. So let's rewrite this to the side for our prime factorization. And think of a prime number that will divide into all three terms. Our primes are 2, 3, 5, 7, and 11. So you might want to jot those down. 2, 3, 5, 7, 11. Of course, there's more beyond that, but those are the most commonly used. So a 2 will go into 12, but it will not go into 9. So we'll have to find a prime number that goes into all three terms. A 3 will do so. So 3 goes into 12x squared, 4x squared. 3 goes into 9x and gives us a 3x. And 3 goes into itself and gives us a 1. Notice we're keeping the signs between each term. For a 4x squared, a 3x, and a 1, there are no other prime numbers that can divide evenly into all three of those. So we are done at this point. So we'll take the number that we divided is our greatest common factor, and then the leftovers will go inside that parentheses. So 4x squared plus 3x plus 1. So this is the factored form of the polynomial that we began with. You could always check that by distributing 3 back through each term to see that you get back to your original problem. Let's look at example number 2. Here we have 40x to the 4th minus 24. So again, we're going to start with doing prime factorization. We have 40x to the 4th minus 24. We'll just rewrite it to the side to do our prime factorization. So choose a prime number that will go into both terms. I'm going to start with 2. 2 goes into 40 20 times. Of course, bring down your x to the 4th. 2 goes into 24 12 times. Of course, keeping the sign in between those terms. We can continue to divide by primes. We're not done just yet. 20 and 12 can be divided by another 2. So 2 into 20 is 10. 2 into 12 is 6. Of course, keeping your variable and keeping your signs. We do need to continue dividing until we can no longer divide by any primes. So we see another 2 will go into 10 and 6. So 2 into 10 gives us a 5. Of course, bringing down our x to the 4th. 2 into 6 is a 3. At this point, we will stop. 5 is a prime, 3 is a prime. There's no prime that can go into both. Because each of those are primes, we are going to stop here. So in order to find our GCF, the numbers out front will be our GCF. So multiply them together. 2 times 2 times 2 is an 8. And then our leftovers, the 5x to the 4th minus 3, that goes inside of our parentheses. Again, you can distribute that 8 through the parentheses to see that it does check out and get you back to the original problem. So our factored form is 8 times 5x to the 4th minus 3. Let's look at example number 3. Here we're going to have 90x to the third minus 50x plus 10. So again, rewrite that off to the side. And divide by primes. Now I know sometimes looking at a problem you could see just looking at it what they have in common, and if that's the case you can just start with that number. However, I do encourage prime factorization because there's times in our work that we have to divide by primes, and we want to have that continuous practice. Excuse me. So let's start by dividing by 2. 2 goes into 90 and gives us a 45. Of course, bringing down our variable. 2 goes into 50 and gives us 25, and again, bring down your variable. And 2 goes into 10 and gives us a 5. Notice we are not done, because if you realize 90, 50, and 10, obviously 10 is what they have in common because they all end in a 0. So 2 is not the greatest common factor. We actually need to go further and divide by another prime. Dividing by 5, we get 9x to the third minus 5x and plus 1. So 2 times 5 gave us that 10 that we probably could have noticed from the beginning was our common factor. So 2 times 5 is a 10, and our leftover goes inside of that parentheses. So this that you have at the bottom of your prime factorization will go inside of your parentheses for your factored form. So 9x to the third minus 5x plus 1. Always be careful with that plus 1 at the end. I commonly see students wanting to leave that off. We cannot leave that off from our answer because 10 times 1 is how we get that last term in this case. So be sure to include that in your final answer in your factored form. Now let's look at how to factor variables as a GCF. Let's recall some exponent properties. We have a to the m over a to the n. Recall that this property told us that we would subtract a to the m minus n. When you divide powers, you subtract their exponents. Also recall that anything to the 0 power equals 1. We will get to a point in our work where we have factored out all of the variables, so we'll have a 0 exponent, and that's going to represent a numerical number 1. And then finally recall the property that a to the m times a to the n, we will need to add the exponents. This will come in handy when we are checking our work, remembering that when we multiply powers, we add our exponents. So let's look at example number 4. We have x to the 7th plus x to the 5th plus x to the 3rd. Well, if we look at the numbers in front of each variable, it is just a 1. So you could factor out a common factor of a 1, but it's really not going to make any difference in your work. But they do have a common factor of variables. So let's take a look and see what that would be. Let's go off to the side and do our prime factorization again. Although this time we're not actually going to be dividing by a prime number, we're going to just be dividing by a variable. So when we divide by variables, remember we subtract the exponents. So I'm dividing by just x, so I'm going to subtract each exponent by 1. So that becomes x to the 6th plus x to the 4th and x squared. But notice I can factor out another variable. I still have more in common, so let's factor out another x. Again, subtracting the exponents when I divide powers, I subtract those exponents. So that becomes x to the 5th, x to the 3rd, and just a plain old x. Of course, that would be x to the 1st. We're not done yet because they still have an x in common. We can divide by another variable, making it become x to the 4th, x to the 3rd, and x to the 0, and this is where this becomes a 1. If we factored out and subtracted 1 from 1, that became x to the 0, and anything to the 0 power equals 1. So we are now done with factoring out our greatest common factor. We have factored out x times x times x, which is really x to the 3rd power. And our leftovers here are x to the 4th, x to the 3rd, and this 1. Of course, including the plus signs between each term. And look, I've already made a mistake. I need to subtract, so this needs to really become x squared, and then the 1. So this brings up a good point. Who wants to individually, one by one, subtract out these variables? You see, as I just did, subtracting can become just so tedious to where you just forget to do one of the variables. So a better way to factor out when we're doing these variables is, again, rewriting it to do your prime factorization and look at the smallest exponent. If you look at the smallest exponent, that will tell you how many they have in common. So x to the 3rd, instead of subtracting them out one at a time and being likely to make a mistake, go ahead and subtract the smallest exponent from each term. So 3 taken from 7 and gives us 4. 3 taken from 5 gives us 2. And then 3 taken from 3 gives us 0, but anything to the 0 power is 1. So this very quickly gets us to our factor form of our leftovers, x to the 4th, x squared, and the 1, of course, with our GCF being an x to the 3rd that we write out front. Let's look at example number 5. We have 29 x to the 5th minus 17 x squared. So this time we have numbers and variables to consider. (29) and 17, see if there is a prime number that will divide into both. There actually is not, because 17 is prime and it will not divide evenly into 29. So we're now just going to look at our variables. We could individually, one by one, factor out these variables. But again, if you look at the smallest exponent, that smallest exponent will tell you how many they have in common. If this one has x to the 5th and this one has x squared, the smallest exponent will be what they have in common. So let's go ahead and factor out both of those at the same time. Of course, the number stays, the 29. We're going to subtract, when you divide powers, go back to your exponent property, when you divide powers, you subtract their exponents, so that becomes x to the 3rd minus, keeping again the 17, keep that number, we've not changed anything about it, and we're going to subtract 2 from 2, and that gives us 0, but anything to the 0 power is 1. We don't need a 1 here. You could say times 1, but that's not unchanged that negative 17 that you already have. So really just leaving it, because you factored those out, you don't need any variables with that 17, or negative 17 rather. So our answers in factored form, we're going to put this x squared out front, and then the 29 x to the 3rd minus 17 as our leftovers. Again, you can always check by distributing this back through the parentheses. So x squared times 29x to the 3rd, recalling our exponent properties of adding those exponents. 2 plus 3 makes 5. And then x squared times negative 17 gives this the negative 17x squared.